The recording has started. So, how was week 2? How was the week 2 lectures? Let us just interact for 5 minutes till people come in, and probably by 4:10 or 4, just about 4:10, we'll start the session. Hey, you can unmute, you can message, you're free to. Don't worry. Okay. Um, there are no questions. Excuse me. Am I audible, right? Am I?
Yes, sir.
Yeah. Okay. So, how was week 2? You have some questions about it? Because we'll go through how we would solve the problem that is there. Sham, can you elaborate? What do you mean by recorded classes only? So are you able to solve the DH parameters problem?
Hi Vivek, uh, it's
Hi
Manish this
Manish.
side. Actually, I have not reached till the DS parameter. I was doing the first topic for the week 2. You can
Okay,
explain.
okay, all right. That's not an issue. Okay, anyway, I'll be covering this. I'll be taking one or two problems, and we'll be working through. One problem we'll extensively work with, and I would show other representation of making the free body diagram, which Ashokan has referred to in the algorithm lecture.
Alright.
So there are multiple ways of making robot schematics. So we would also go through one way that is mostly followed.
Okay.
So yeah, so probably this lecture will help you understand what he means in DH algorithm. He has
Yes.
written it rigorously so that you don't miss out if any other new robot comes in a new joint way of a new joint comes in, and you have a robot which has such a new joint.
Alright.
You can use that DH algorithm and it will still work in those cases, most of the cases. So we will be making it much simpler so that our focus stays in revolute joints and prismatic joints. So that way we would have understanding in the basics. Okay.
Oh, okay.
So so apart from Manish, there is anyone else who has gone through lectures and has some doubts in DH parameter in other lectures also? Because DH parameter is the only problem that they have given in your assignment. But I'm free to take up any other question because everything else is a theory. Yeah. So I'm suspecting that most of us will have a problem with DH parameters because we are not used to this kind of representation. Yeah.
Yes.
Okay. So it's almost 4:05. Okay. So let us start. If people join in, that's all right. Uh, if if they miss out something, you can always ask. I can go back to the part you have missed out, and I can explain again. So your Denavit-Hartenberg parameter, that stands for DH parameters, is a way of assigning axes. Okay, let me start writing. One is assign axes slash frames to your rigid body, rigid bodies, and second is having parameters that map from one axis or a frame to the other, right? So mapping of one axis to the other. So this is what your DH parameter does. I guess the first few lectures were about joints and links. So a simple definition for joint and link would be, if I have two joints, let us say a joint is something that gives you a degree of freedom. Anything that connects two joints, any one single entity that connects two joints is a link. And the corollary of this is that two links, two adjacent links, the intersection of it is a joint, right? So let me take it L1, L2. Now what we are interested in is kinematics, which actually is cinematics, right? Capturing, that essentially means capturing frames or motion. Yes. Yeah, people, last live session recording is not posted in course page. Pratyush, I guess the sessions we are taking are not going to be posted on the course page. It will be posted on YouTube link, and this link must be shared from the NPTEL team. I'm not sure, but I'll try to leave a link here. Probably you can find it easily. Okay, I'll leave the link in the end of the session, Pratyush. Is that okay? Yeah. So what we are interested is in kinematics, like we want to capture frames in between. Let's take a robot, a simple 3R robot. How we name it is, here's a revolute, here's a revolute, here's a revolute. There are 3Rs that are in series, right? So what we are interested in is the kinematics of it, like how it moves, right? How does it, or how can it move, right? So this has a workspace. If I'm interested in where this end effector, right, end effector is can go, if I'm interested in that, that is what would lead me to kinematics. So in robot, we have two kinematics that we are at most interested in, is direct kinematics and inverse, inverse kinematics, right? What direct kinematics gives you is the position of end effector. Let's take it as EE. You get position of end effector given. Let me use another color for given. Uh, okay. Given joint parameters. So recalling what is a joint, I'll go slowly, I guess. Refresh, that's not that good in Gmeet. Okay. So going back to what is a joint is intersection between two links. How two links rotate about each other is the joint, is a characteristic of the joint. So given this joint parameter, let's take J1, J2, whatever they be. They can be R, they can be S, they can be prismatic. For prismatic, we have a different symbol. I'll come to that. So given those joint parameters are spherical S, so you have theta x, theta y, theta z. Here it is only one theta about the axis k, let us take. and prismatic, we have some d displacement in the k axis, right? Given this joint parameter, I am interested in finding the end effector position. This is my direct kinematics. So this is a result of your DH parameter. Just from your DH parameter, you will get the position of direct position of your end effector. Now here, what I have, what I'm interested is getting, yeah, getting joint parameters given yeah, given my end effector location. Difference between end of arm and end effector. Yeah, here the end of arm and end effector is the same. Technically, your end effector will have, it can have n degrees of freedom. It's on the end effector. End effector is an entire entity of itself. Here is an end of arm and end effector, both are the same, right? So yeah, difference is that the end of arm is till let's take a robot is 6 DOF. It means it has 6 degrees of freedom, and all those 6 degrees of freedom are coming from the arm only, all the arms that it has, all the links. So that is yeah, that is where you can say end of arm is that end of the robot. At the arm, you can put up at the end of the arm, you can put up an end effector. If you don't have anything, that also serves as your end effector. Yeah. Okay. So coming to DH parameter, how given a robot, let's take given something like this, some robot, right? Right. So let me admit few new people. Okay. For access, let us one second. Give me a second. Yeah. Access, let us use red. So this is my base frame from which everything in the workspace. This is my workspace, right? Everything in the workspace I'm interested in will be denoted from this frame. Let's take this is ground, uh, Z ground, and this is my X ground frame. From there, we assign frames to all these links so that we are interested to come at the end of the arm, from where again there is a series of transformation that an end effector will have. If I have no degrees of freedom and no offsets, degrees of freedom, number of degrees of freedom is 0, um, no offsets. So my end effector is almost my end of arm, right? So we are interested in this position since this end effector is an entire entity of itself. I shared a jam file with the meeting. Okay. Mhm. Raj Mandal, I cannot access your Jamboard, I guess. Is there any doubt? You can let me know. You can stop me at any time, right? If you're not able to follow, if it is my voice is lagging or there is some noise, let me know. Okay. Yeah. So yeah. So what we are interested in is first getting the frames, right? So for this, we would get to schematics, right? We want to make it as minimalistic as possible for us to understand. So let me give you one form of schematic which is widely followed so that you understand the revolute or the spherical joint, how it spans over a schematic. right? So one way of utilizing this robot in a schematic is that I assign something like a cylinder, and this tells me that it's a revolute joint about that axis, right? So the first joint that you see here, this particular entity, can rotate about this axis, although this frame is not on this body, right? So this is my base frame. So let me take Z0. Why am I taking the joint or the axis of rotation as Z0 or Z axis? Is that in robotics we follow this convention very often, is that Z is my joint axis, right? The joint's characteristic will always be in the Z axis. If I have a prismatic is given like a dashpot. Okay, let me not use it that way, but then yeah, prismatic. Okay, so when I have a prismatic joint, again the axis will be Z dot. When we have a slider, right, in a 4 bar or a 3 bar linkage, when we have a slider, right, this axis will be denoted as Z axis, right? So the characteristic of the joint will denote its axis. So one way of representing that robot will be something like this. One revolute is here, right? Then another revolute is here, but has changed axis, right? There is another revolute here, right? But remains the same axis as the before. So this is how I would reach to end effect. So this is one way of giving schematic. The one that is followed in NPTEL lectures by Ashokan, I'd be using that to solve a problem, and that way, probably it will be easy for you to attempt assignment, and it will not be overwhelming with new convention, new way of putting schema. So there is a problem in your assignment that has something like this, that your oh, one second, let me just see that assignment so that I don't confuse you. Yeah. Okay. So x0 is here. Um, you have your z0 here. Z cross x. Y will point this way. Y0 here, right? And then there is, this is your um, J1. This is your first joint with a frame starting with 0. So let us take it, keep it as frame 0. So this denotes frame, right? X underscore I denotes the axis, yeah, I of the frame, right? So you have your at J2 you have another frame which is something like this, yeah. And your third joint has an axis something like this, x2 here, x cross y into the board, z2, yeah. So this is a problem that is given in one of your previous run. Maybe it will not be identical, but we'll solve this so that you get an idea of how it needs to be done. This is 60 centimeters. So I think that quite a, yeah, let me come back to, yeah, give me a second. Yes. I think quite a lot of you guys have not seen DH algorithm lecture. Is that correct?
Yes, sir.
Okay. So let me just even tell you that how each of those parameters work. So in DH parameter at any joint, at at any joint, we have four parameters. Okay. So the first parameter is joint rotation, right? So this is nothing but rotation about about joint axis. Now recall what is joint axis. Joint axis, people who have came late, joint axis is something where my z is pointing, right? So once I get this schematic, like this schematic is given, yeah, I'll be sharing all of these on the drive. I'll in the end I'll probably give you the links. This is NPTEL's responsibility to send you, the NPTEL team's responsibility to send you the links. So nevertheless, I'll post it here for your reference. Okay. So the joint rotation is nothing but the rotation about your joint axis. So if your axis is a prismatic axis, uh, it's not going to have any joint rotation. So what do we do with that? So there is something called joint distance. Now for a prismatic axis, your joint distance plays a role. So distance traveled or traversed. Traveled is for a prismatic axis. Traversed is when you don't have a prismatic axis, but you have some z offset. So your frame has traversed that distance, or distance traveled or traversed about. Let's not do about, along along your joint axis, right? So the third thing is link angle or your twist angle, right? So this angle rotates or orients the z axis. So from one frame to another, when your z axis are not oriented, they are not the same, they are not parallel, your your twist angle comes into picture. So there is some twist that has happened. Let's take your arm. If you can move it across a plane, you will see all of them are having the same z axis. If you can have it in a plane, you move your arm. The moment it goes out of plane, you know that you are twisting somewhere. So that is the twist angle that we are talking about, right? So the fourth one is link distance. So this is nothing but the distance that has traveled along two normals, along two normals. Let's take z I minus 1, and this is some other axis along two normals that is not in the joint axis, right? So I'll show you how the link distance is. Probably with this words, it is little confusing, but then we'll come to that. Okay, so there are four parameters. These are given in this way. Okay, let me just put it here. Joint rotation is denoted as theta, joint distance as d, link or twist angle as alpha, link distance as a. So this is alpha a, right? Alphabet A. This is Greek alpha, right? This is alphabet D, and this is Greek theta, right? Okay. Now we'll come and see how we give accesses or we assign frames to any body. So let us take the example that I had given already. So something like this, right? So here you can see that this is a rotational joint, a revolute joint. So the axis is going to point in the direction where the rotation happens, right? If it's going to rotate about this, this is going to be my z naught. Now you're free to have your x naught, right? We generally keep x naught, your x direction, as a twist axis, and we generally keep our link lengths for a revolute. We'll keep our link length along x naught. So from here it comes here. So let me take, this is my z1, because it's rotating about this point, right? And this is my z2, right? Z2, sorry. So this is my link direction. I will put my link, x2, x1, my mistake, x1. This is frame 1, this is frame 0. Yeah. So in frame 1, at this center, I have x1, z1 and x1. And this is z2. x2 will be pointing somewhere here. I'll write it little legible. Z. Okay. So this is how we generally give our frames to any link. Although in the lecture he has mentioned that it is not necessary to have your frame of a link at the origin of the link. It is not necessary. Although we follow that because the subsequent derivation for velocity, acceleration for a moving body would become more convenient if we have such a representation. But nevertheless, uh, our primary focus will be to solve such problems, because once we get an idea of how it needs to be done, all the frames and everything else will just be secondary, right? So you need to follow one convention only. So you are free to adapt to any convention. So okay, yeah. So we'll just come to this problem that we have in our hands, and we'll try to denote what is the joint axis, what is the joint rotation, joint distance, twist. Yeah, Manisha. Yeah, you can raise your questions.
Uh, Thank you. Yes, in that, in joint 2 space, you have created a frame. Is that frame 1 you have written there?
Joint 2, I have written frame 1. Yes.
Okay.
Joint 2, joint 1, joint 3.
Can you explain this rotation again, because I am unable to visualize the third joint motion?
Third joint.
Yeah.
Okay. Let me, sorry.
Go ahead. That's, I think, some glitch.
Okay. So how is this link connected? Let's take, this is a link. Okay. Let me just draw it as a straight line. Yeah. Okay. This is my x1. It's going to rotate about this axis, right? Can you understand? Sorry, z1.
Yes,
Manish?
yes, yes, yes. I am
Yeah.
getting.
This is nothing but parallel to Z1,
Okay.
right?
Yes.
For a SCARA configuration, this we have a robot or a configuration or a Revolute pair like this for a SCARA configuration. So this is a popular robot. You can look at. So what we have here is both the z-axis are parallel to each other, but at a different origin. Are you able to follow?
Yes, yes. I'm getting here. Yes.
Yeah. So you're getting it right. Joint
Yes,
three.
yes. They are
This is
parallel
my
and different origin.
yeah. This
Yes.
is my x2. Here, this is my x1. So this is a easy convention to follow. Although if you rigorously go through DH parameters, you can give for any robot. But it is convenient to go this way, having an origin or having a rule for an origin to be fixed in a link. So you will see as the lectures or as weeks progress, you will be able to see and you will be able to appreciate having a frame at the start of the link. So it's not necessary though. Yeah. So we will come to the problem that is given to us. We don't have to show all the three axes only because here we work with something called orthonormal axes. Axes. Yeah. What we mean by orthonormal, if I have any two, I can do the cross product and get the third one. Right? So let me take from the problem that was given to us. I'll write it little below so that we have space. Okay, let me make it a little bigger also. X0, this is Z0. Okay, and the second, the first frame that we have is here, right? So let me denote the origin also. This is X1, this is Z1, right? We have another joint about which the frame is oh, okay, about which the frame is Z2 X2. Okay, so this is frame 0, frame 1, frame 2. Okay, now here you can see that I am not denoting y axis because your it follows something like this: x cross y axis, right, is equal to your z axis. All of them are unit vectors. Y cross z is equal to x axis, and your z cross x is your y axis. So since I have z and x, y is not going to go anywhere. It's going to remain orthonormal, right, to these both. So since my axes that I'm interested in is joint and twist, that's why I'm only denoting those. Right? Is that clear? I
Yes,
think
yes.
here you can ask doubts, because if this is this part is not clear, then we will not be able to get a correct representation. And that, although for your axis or your way of denoting axes, you may get a good I mean, you may get correct solution out of it, but others may not comprehend what you have written. So it's always good to follow a convention. So that's why we are all going with orthonormal axes. So I'm only denoting two axes here. Now here, let us see the first question that we asked. So DH parameter is all about this question if I have to boil it down. And this is my interpretation. although this is not something huge or great, but then it is an interpretation that is easy to understand. What it takes for you to go from frame 0 to frame 1, that is the basic question that we ask. What is the series of transformation that you want to do so that you reach from 0 frame to 1 frame, right? So that is the question. And the second question is, can you make this transformation consistent? What I mean by consistent is that you do this with any two axes, from like any two consecutive axes. I must get it must work, right? So that is the objective. So here the first question is what it takes to reach from frame I minus 1 to frame I, right? The second question is, can you be consistent, right? These are the two essential questions that we ask. So let me just get to the first question. So we can discuss here what takes from 0 to 1. How would I go from 0 to 1? Just look at the figure and uh, we can discuss here. Everyone can, perhaps one by one, you can open your mic and you can talk. If nobody is ready to talk, you can just let me know over messages, so I'll just skip it. Okay. All right. Okay, so let me just explain it. So here you can see that about x-axis I don't have to do anything to like only in terms of the orientation. Talking in terms of orientation, I don't have to do anything about x-axis, x0 axis, to reach to x or to resemble x1 axis, right? So let me just make it that way. Here you can see x0, z0, right, x1, z1. In terms of orientation only, the offset I'll deal with later. I am not doing anything, right? So what does that mean? My joint axis, that is about z0, I am not doing any rotation, right? So theta 1, yeah, theta 1 is 0. Wait, I've not given indices, right? Okay, I'll explain the indices also. Now theta 1, because I'm going from frame 0 to first frame, my eye will be dependent on the first frame. So about z0, I do theta 1 rotation of 0 degrees to reach z1, to reach z1, right? About x0, x0, right? Oh, okay, I did a small mistake. So I do no rotation about z0 to reach at x1, because if I had done any rotation, let's take I have done some rotation about z0. So let's take 30-degree of rotation I've done, which is anti-clockwise. Okay, I've done anti-clockwise sense. Yeah, this is z0. X will be something like this, right? So here, this, if I had an z1 x1 axis like this, I would say my theta rotation about joint axis should be 30, right? Is that understood? Since I am not doing anything, so about z0, if I do 0 rotation, I reach to x1. So if I do 30, I will reach to x1, which is 30-degree offset, right? From this axis, that is x0, this will be 30 degree, right? So this is about that. And about x0 theta I do alpha I do 0 degree rotation to reach z1. Now let's take x0, right? So about yeah, here x1, about the transformed axis. After I have done z axis rotation, I get my x1. Let's take when I have done for 30, I have my x1 here. About x1, like first we have done z, then we get some x. About that x we rotate to get another z, right? This is I minus 1, we get xi. From xi, when we rotate, we get zi. Okay, so about xi, x1, if I am rotating 0 degrees, I will reach to, yeah, z1, right? So here you can see that if I rotate x0, this axis z0, by, let's take alpha, so this will be something. Oh, I'm sorry. Yeah, let me just put this here. Yeah. Mm. Yeah. So if I have axis something like this, I've done alpha rotation, so this will come out something like this, right? Next one, Z. Let's keep it like that. After this rotation, right? If this was x0, my x0, sorry, z0, x0 is like this. After 0 degree rotation, I get my x1 coinciding with x0. Now about x1, if I'm doing an alpha rotation, this will become my x1. Z1, I'm sorry, I keep doing this. This becomes my z1, right? So this is nothing but my twist angle. Okay, so this is the sequence that you can take it, that this is what we do when we have z I minus 1 frame. We rotate some theta, we get an x I, the new frames x. About that, when you do a rotation of alpha, then only you get your final frame xi. So the moment you have got zi, the moment you have got zi xi, yi becomes determinant, right? Because it is orthonormal. So this is the concept. And now coming to the distances, here when we have something like this, x0, z0, and here x1, x1, z1. Yeah, I keep interchanging this. Yeah. Now the distance about x-axis. Yeah. So the distance if I travel along x-axis, along z-axis is called my joint distance, right? But here you can see that these two z-axes are parallel. They are never going to meet. So I cannot travel from one like z0 axis and reach z1 or origin of the next frame. I cannot do that, and hence my distance d1 would become 0, right? Now let us take for link distance. Link distance, like since my z axes are parallel, what I will have is draw common normal, and distance between those two normals, right? Or like this also you can draw, and distance between these two normals is nothing but my link distance, that is alpha 1, which is in this case 60 centimeter. Let's just keep it 600 mm, right? SI unit. Okay. So now we are clear about all the terms that we need to form a DH table. So let me just get into it. Can I copy this frame? I don't think so. Yeah, let me try. Copy, paste. Oh, ooh, okay, cool.
Excuse me.
Sorry?
Yeah, I have a question.
Yeah, Raman, go ahead.
So right now the frame 0 and frame 1,
Yeah,
they are oriented in the same direction, right?
yeah, they are oriented in the same direction,
But they are
but they are,
spatially apart.
or yeah, spatially apart.
Yeah,
Origin is not the same.
yeah,
Yeah,
that's it, right? So in order to
yeah,
go from frame 0 to frame 1, we
mm,
will the transformation matrix would look like an R equal to identity matrix, and then
yes,
the distance that we have to move, it will be some x 0 0, that it will be of that kind, right?
of that kind. True. It will
Yeah,
be an offset.
yeah. So
Yeah.
what you are explaining there, like z I, we have to do rotate by theta, and then
Mhm.
that will give us 2xi. It is not possible in this case, right? In whatever angle you rotate about z axis, since they are already aligned,
No, I'm
z will
doing
not
that.
go to xi, right?
It will go to xi. No, 0 degrees.
No, are you suggesting that about z axis, if I rotate my z axis will align to x axis?
So let's take it like this. So when I have one frame, right? Okay, sorry. Let me get to pen. Yeah. So this is my x0,
Okay.
z0, right?
Yeah.
Had I had axis something like this, right? Now
Okay.
you know that your z-axis is coinciding is as in they're
Yeah.
parallel,
Yeah. 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 I understand.
but the
Okay. You are
x-axis is not.
explaining for a general sense, right? In the above example.
Yeah, I'm giving you a general sense so that
Okay. Okay.
you can substitute your general sense with some values. Like in our
Okay.
case, we are not rotating, but we are rotating by 0 degrees or by
Okay.
360 degrees. It
Okay.
remains the same.
Yeah.
You're getting it,
Yeah. Yeah.
right? So when you do one complete rotation, the x0 will come back to x1. So you can have a multiple of pi, 2 pi,
Okay.
right? Even multiple of pi,
Yeah. Right.
right? So that is the like the concept that we are evolving around. Yeah.
Okay. So
So here,
initially we rotate about z axis, then about x axis. So that is the sequence we want to follow.
yes, first
Or you
z,
can
then
rotate.
when we rotate about zi minus 1, we will get xi,
Yeah.
right? The moment I rotate about xi, I get zi. The
Yeah.
moment I have these both, I have yi. That's the concept,
Yeah. Okay.
right? We have three unknowns. So we are getting one, then we are using one to get the other. The
Yeah.
moment we have done these two, we get the third one. Now our frame is fixed.
Mm. Yeah.
Fixed in the sense it's not going to, there is no ambiguity in that frame. Okay. So let us just get into making the DH table. I guess you have taken quite a lot of time, but I think it must have been useful. Once you go through the lecture, probably it will become much easier. So we have theta I, alpha I, a I, b I, right? So this is my table. This is my DH table. Now I is going to span number of links, 1, 2. There are only two links. So this is link 1, this is link 2. So I is going to span for 2 only. So we have I is equal to 1, I is equal to 2. Now what it takes, the primary question we ask, what it takes from 0 to 1. Now I am doing a theta of 0 rotation. About x also, now the new x I have formed from if I do zero rotation about x1 z0, I get x1. About this also I'm doing zero rotation, right? Now how did this origin reach here? About z axis, have I traveled anything? Z0 axis? No. Again, di is 0. About x0, or let's take any two normals from these two frame, have I traveled something? Yes, I have. 600 mm. Okay, in your assignment it is centimeter, but I always follow mm. Yeah, so 600 mm. So this is my uh, first row entry of the table. Now what it takes, now we again ask the question, what it takes to go from 1 to 2, right? Now here is the trick, right? Here is the trick for that question. Now here you see that although it's straightforward, but here you can see that about z1 I have done a counterclockwise sense 90 degree, that is plus 90 degree I have rotated. I get z2, right? About z2, how much I have rotated? There is no need of rotation, so zero rotation has been done about x2 to arrive at z2, right? So theta is 0. No, sorry, I mean theta is 90 degrees. I have done plus 90 degrees. So z1 came and became z1 gave me x2, and about x2, how much degrees I have rotated? 0. Still we are not done. Why? Because our origins are apart, right? And this distance is 35 centimeter. Will come and will fill that entry. About x1, have I moved anything? About z1, sorry, I mean about z1, have I moved anything? Have I moved any far? No. So again we'll get d2 as 0, and then we will construct two normals in these two frame, and along those two parallel normals, have we traveled something? Yes, we have. So that is 35 double, sorry, 350 mm, right? 350 mm. So this completes your table, and this is all that the assignment asks. But let us get to some complicated example, because this is it felt straightforward, right? So let's take from frame 1. Yeah, the frame 1 is something like this: x1, z1, right? And frame 2. This is just for understanding that we are taking frames like this, right? This is not part of your assignment. I guess your assignment will revolve mostly around getting these parameter. Twist will generally be avoided, but will take up a case where we'll have twist axis, right? So let us take our z2 like this, right? And x2 like this. Now how will the transformation need to be done so that I reach from frame 1 to frame 2? This is similar to the previous one, but the only thing we have done is revolved z2, right? So here you can see that the initial set of things what we have done remains the same, right? x1. So I'm drawing an intermediate frame so that it is easier for you to understand. All the origins remain the same, right? I'm just making an intermediate frame. What is intermediate frame? Instead of doing series of rotation, transformation, sorry, translation at once, I am doing one by one of everything, right? So first thing what we do here is about z axis, z1 axis, I am rotating by 90, right? So I would get, so let me make it solid line. I would get my z 1 like this, and my new axis will form something like this, x2. Right, now I want to get z2. Z2 looks like this, solid line z2. This is x2. Yeah. Now I want my z1 to transform to z2. Right, what will I do now? I will do a rotation which is again in counterclockwise sense, that is plus 90 degrees. So always counterclockwise sense, you look at the axis, you look it from here. If I have an axis like this, right, you look from here, right, and see how the frame, this axis is rotating either like this or like this. If this is counterclockwise sense, this is clockwise sense. Okay, this is trivial, but I'm just making it clear that you look into the axis, not along the axis. You don't look from here, right? This is wrong. You look into the axis, you look straight on it, and then you find the rotation. Yeah, so this is just a touch that I want to give so that you don't forget. Yeah, so I need to do a 90-degree rotation to come to z2. So what I have done in the table, 2 theta 2 alpha 2 d2 a2, right? So theta 2 is 90, alpha 2 is also 90 here, right? So this is what we have done. First we do z rotation about zi minus 1, we get xi, about xi we get zi, and now everything is fixed. So there is no ambiguity in the frame, in the resultant frame. So this is an intermediate frame, right? Intermediate frame, right? 90. And D and A remains the same. D2 is 0. A2 we have moved along this normal, right? I guess yeah. Someone has a doubt? No? Okay. So let us now look at how from this DH table, let's take, I have an entry I have theta I, alpha I, di, ai. Based on this entry, people are still joining after 450. That's really nice to see. Okay, we have this as an entry. Okay, this is one row of your DH table. This is one row of your DH table. From this, how do we get to a transformation matrix? Sir, how D2 is 0 here? Can you please explain? Okay, now see, again, you look at it this way. Okay, I'll give you an example where D2 is not 0. Okay, Togeshwar. Okay, I can call you Krishna, right? Yeah. So let me give you an example where uh, D2 is not 0. All right. So probably with that you will be able to appreciate what we are doing. So this is Z1. Now my frame is here. Okay, Z2. Now you understand what I have done. There again, this point, right? It's not collinear with these two axes, or in x2 axis. This point does not lie in the x2 axis. Right? Now let us make an intermediate frame. Here, right? I have z1 and x2. Right? The same thing I have done. Rotated about 90 degree. I get x2. But now what I have done? I have also moved d distance. Krishna, does this solve what questions you had? Now along x, sorry, sorry, z1 I have moved d1. uh, Actually it will not be d1, d2, right? Here you can see that where did that go? um, yeah, I have not mentioned that. Okay, let me just do it. Okay, now when you move from using zi minus 1, when you move from z uh, I a distance, that will always follow the next frame. So di will be a distance from zi minus 1, right? Along zi I minus 1, along zi minus 1, right? This is crucial. So here, yeah. So for an entry, so let me take for an entry. Yeah, let me take it an arbitrary entry where we have I minus 1. This is x I minus 1. This is z I minus 1. So it has moved some, right, distance di. So I can give an intermediate frame as it. Okay, the frame is it, intermediate frame. Okay, here, right, my zit is something like this, and I've also made a rotation, right? So let me put the rotation also 90 degrees. Should I make 90 or arbitrary? Let me make it arbitrary so that it's more clear, right? So theta I, right? So because of this rotation, my xi I will get here. Okay. So this is my intermediate frame. This is my intermediate z axis. I've got my x axis. From here, again along this xi direction, I move ai distance, right? And this is the final ith frame I am interested in, right? xi. But again, after moving ai, I am doing a rotation about xi, that is 90 degree to arrive. Let me make it into a solid line, zi. So now all the parameters are there. So let me make it arbitrary, alpha I. Okay. So what the series of like the series of steps we have taken to reach there, let us preserve this. What we have done, z rotation, zi minus 1, theta I rotation, right? Z I minus 1. Okay, we have not. Okay, let me just put it this way. Give me a second. First, we didn't rotate. First, we moved. Right. Let us preserve it. Z I minus 1. I went di distance. Right. Traveled. Traversed. Sorry. Traversed. Yeah. Z I minus 1. I have done theta I rotation. After that, what I have done, xi I have got because of this rotation. From this, I have done again ai travel, right? Then, okay, someone had to be admitted. Okay, all right. Then about um, xi, I have done alpha I rotation, right? So this is nothing but rz rotation, rz in a rotation matrix format. This is rx, right? How will we get our transformation matrix? Let's take ti minus 1. From ti minus 1, we go to the intermediate frame. How do we go there? We have done a rotation. First, we have done a distance travel. Let's go step by step. Sorry, let's go step by step. We have done a distance travel, that is di 1, right? Now we have also done a rotation of theta I. So we will have a rz theta, that is c theta minus sine theta 0, sine theta cos theta 0, 0, 0, 1. This is how a transformation matrix will be. Although, let me just reiterate. Okay, I'm telling it for the first time. Let me just tell it. The transformation matrix is not asked in your current assignment. This is like we are doing as a part so that Raman had also asked. So let me just cover it all together from an intermediate frame point of view, how we get to the final transformation matrix. So I'll come to that. Yeah. So if people are getting late, you can leave because our session is still 5. People are getting late. They can leave because this part, what we are doing now is a little extra. Probably you will be covering this in the next week. Right. Yeah. So from intermediate frame, how do we reach I? Like we have done this set of transformation, right? Right. This is from IT to I, and this is from I minus 1, I minus 1 to IT. That's the intermediate frame. Right? Okay. Now here, what I have done, I have traveled a distance of AI 0, 0, 1. As simple as that. Then what I have done, I have done also a rotation about x. That is nothing but C alpha minus sin alpha, cos alpha minus sin alpha, 0, sin alpha, cos alpha, 0, 0, 0. Yeah. So, and how do I reach t I minus 1 to I? This is nothing but product of matrix multiplication of this. Right. So let us just multiply it and get to the final expression. Right. So here, right, see, okay, I'm sorry, 1, 0, 0, 0 C alpha minus sin alpha, cos alpha minus sin alpha, 0 sin alpha, cos alpha, AI 0, 0, 1, 0, 0, 0. This matrix multiplication with cos theta minus sin theta, 0, sin theta, cos theta, 0, 0, 0, 1, 0, 0, d1, di, 0, 0, 0, 1. Right? By multiplying this, we'll get an elegant form of transformation matrix, and we'll see something that that gives us directly something. So let us go through this rigor patiently, so that we'll get get to what we are coming. Now this I'll link it to what from where we started this session. Okay. Right. So for the convenience, let's do it. C theta minus sin theta, 0 AI. Then you have sin theta cos alpha minus cos theta sin alpha minus sin alpha minus sin alpha di. Then the second row is sin theta sin alpha cos theta sin alpha, right? And this one is cos alpha. We have di cos alpha. The other matrix would be this. Now here you can clearly see that this row, sorry, this column, right? Let me highlight it with another color. Okay. This row is the direct kinematics of your robot. If you have done T 0 to the nth frame, right, the matrix that you will get 4 by 4, the fourth vector is your direct kinematics. Given an alpha, I can find, given alpha, AI, and DI, I can find where my end effector is. At least the home position I can find. So this is the direct kinematics. For inverse kinematics, we'll have to do an inverse here. You get the point here. We have to do an inverse here. Based on that inverse, we will get another matrix. That matrix vector will give us inverse kinematics. So this is just a hint towards the next lecture. With this, I'll just complete. This is all I had for today. I'll be sharing this PDF file with you, and yeah, I hope NPTEL is sending you the links. If not, let me just put it here. Please bear with me. I'll just go to another screen. Exit full screen. Um, yeah, drive. And, why would I drive into a movie theater? Okay, wait. Let me just give Google Drive. Let me just put the link on the chat so that it's convenient. Yeah, give me a second. So if there is any question, you can ask right away. I know it is little overwhelming to what we the new conventions. If it is not, well and good. If it is, then I think I can take up questions. We can, yeah. Any questions? I cannot see your chat window because I'm in another browser. You can open your mic and let me know. And turn on your mic and speak.
Excuse me, sir.
Yeah, tell me. Yeah, Uma, tell me.
So, in the sum which we found out, we DH parameters.
Yeah. I've lost you, Uma.
So, in the sum where we found out DH parameters, is
Am I losing her voice, or is this for everyone? If anyone has got through her what she wanted to tell, can someone post it on messages? Okay, let me just share the videos also. Give me a second for that also. Give me a minute for that. Um, no, okay.
Sir,
Yeah, tell me.
sir, can you solve a problem for me, sir? I can't get the solution.
Yeah, we have solved one particular problem, right?
Sir,
we have been through one problem, right? So you have a problem in your mind. I can quickly go through that.
Yes, sir. From the assignment, I got some doubts, sir.
Yeah, yeah. Tell me, please go ahead.
Sir, for a tooltip having composite rotation of yaw 90 degrees, pitch 45, and roll 60, find the
Yeah.
resulting composite matrix.
Okay. So this is from one, right? We
Yes,
are
sir.
in week
Yes, sir.
two. Okay. Let me anyway put it through. Okay. So you have your what was the question? Your pitch roll or your roll pitch?
Sir, yaw pitch roll, sir.
Your pitch roll. Okay. So remember like this: your is z axis, y axis, x axis. Your pitch roll. Okay. So now this is a subsequent like transformation. They are not done from ground frame. Let me just put it, not from the fixed frame, right? This was done. It was told in lecture. So you can. It was told in lecture that it was from ground frame. It is not. It is from the sequential rotation that you do. Okay. X. Okay. X cross z. No, z cross x. Y will be this direction. Yeah. Sorry. Okay.
Yes,
Now
sir.
for your pitch roll rotation, what you do is that first along z axis you do some rotation theta, whatever they have given you. You will have rz, right? A rotation matrix of rz about theta rotation, right? Theta 1, theta z, let us make it. Now you will have then you will get some axis. Axis will become something like this, right? After that rotation, are you able to follow?
Yes, sir.
Yeah. From this axis, you use this y axis and rotate about y axis. That is theta y. So you will get something like this, right?
Yes, sir.
About x axis now, you rotate something. That is theta x. That is your pitch rotation. This is sorry, roll rotation. Sorry, roll rotation. This is pitch rotation. This is your rotation. Okay.
Okay, sir. Okay, sir.
Now your composite matrix will look like this: Rx, theta x, Ry, theta y, Rz, theta z. Right? This will be your composite rotation matrix. Rotation ypr will be something like Rx, Ry, Rz. Right?
Okay, sir.
Yeah. If you do this, you'll get it. Mhm.
Thank you, sir.
Okay,
Yeah,
I
I have
don't have
small.
the. Yeah, sure. Go ahead. Go ahead. I
Yeah,
don't
in
have
the
the link.
for the above example which you have told,
Okay, which one? I'm
the
scrolling up. You stop
matrix.
me.
Yeah, this one. For this thing, yeah.
Which one?
If I try to plug in the values,
Uh huh.
and then if I try to generally form a transformation matrix, what I
Uh
feel is like Ti minus 1 to Ti.
huh.
The rotation matrix is something like 0 1 0 1 0 0 0 0 1. Is that correct?
Okay. Yeah, okay. Wait a second. Can you repeat that matrix? Tell me.
0 1 0.
Rotation. Zero, 1 0.
Uh, which one we are seeing? Ah, okay, yeah, yeah. 0 1 0 1 0 0
0 1 0 1 0 0
0 0 1.
0 0 1. Okay. Compare these two frame now.
Yeah.
Right.
No, not for this one.
Then
Okay, both are same, right? Yeah, 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 yeah.
both are
Okay.
same. Yeah. Compare for these. Okay. Okay. Sorry. No, they
Yeah,
are not the same.
below.
No. Yeah. This one. This one. This one.
Ah, yeah, yeah. Okay. This is
Right.
also
1 0 0 0 0 1. Now
yeah.
compare this frame and this frame. Now you can see that your this is resultant, right? Now
Yeah.
your
Oh,
x-axis has become nothing but your y-axis, right?
yeah,
So that
yeah,
is
yeah.
0 1 0.
Yeah,
Okay.
this is correct, right?
X. Yeah, this is correct. See, and your y-axis, which was before here, now it became like x-axis, so it is
Exactly.
here,
Yeah. True.
right? Now your
Okay.
z-axis, you can see it where it was, it is same, it is
Okay.
here.
Now for the same thing, if I have to write the translation matter, I mean translation parameters,
Okay.
so it would be something like 0, AI, and DI, right? For
No,
the
AI
offset
0D.
version, because we have moved
Huh.
along the y-axis of the initial
Yes,
frame, right?
yes.
So it would be 0, AI, DI.
Yes, it will be 0 AIDI. So this
Yeah,
is
but for
with
the
respect to,
transformation matter, okay,
yeah, this is with respect to tooltip.
yeah, that is like Ti minus 1 to Ti, whatever
Hmm.
we are trying to
Yeah,
this.
yeah.
But if you
Yes.
plug in the values of thetas and alphas, which are both 90,
Mm-hmm.
we are not ending up with the same thing, I guess. Minus sine theta would be minus sine minus 1, right?
Uh, I'm not able to follow.
No, this transformation
Theta is,
matrix, whatever we have derived,
ah,
c theta minus s theta 0
okay,
AI.
okay. I'm really sorry. No. This is not tooltip. See, there is sequence of transformation here. Like 0 to 1 you have went, then 1 to 2 also you have went, right? So you
But
need to multiply again T01 to T1. Sorry, you have to do
no,
this one
this
also. No?
no, this is for we did for a I mean intermediate frame, but essentially we are looking at that offset version wala this thing only, right?
No, my
This
dear.
this transformation matrix, where does it take me from which frame to which frame?
Okay, let me be clear here.
Yeah,
It
uh,
takes you from this frame to this frame.
from that frame to that frame.
Not from ground frame. For ground frame, you have to do something like this.
No, that is
Yes.
T I T to T I minus one, right?
Which one?
The one which you are telling. Just can you scroll over?
Yeah.
Yeah. So here that whatever we are seeing, that is from IT frame to
Hmm.
I frame. So
Yeah.
that
Like
transformation matrix is like T I T to I.
TIT to I. Yes.
What we found out is Ti minus 1 to I.
Hmm. Yes.
Okay. The transformation
Yes.
matrix which we wrote above is for
Hmm.
Ti minus 1 to Ti, right?
Yes.
Right. So now if we plug in the values over here, it should match the one which we wrote above.
No, because there is one more frame. No, there are two frame transformation from 0 to 1, 1 to 2. Right?
But
One is not an
essentially,
intermediate frame. One is not an intermediate frame.
okay, but whatever transformation matrix which I wrote, I mean, which I told just now,
Yeah.
that is from 0 to 2, right?
What you told is not. Yeah, it's from 0 to 2. Yes, your AI will come to your y-axis. True. Yes, it will come if you do one more sequence of rotation. See here it is. See now if I take I as one. Okay, let me make I also. That is confusing, I guess. Right.
Okay.
So only for one row this will give you one row from your DH table, right? This particular matrix that we have got, it is for one row of your DH table. Our original problem had two rows of DH table, right? You have to do for two, like this: t from 0 to 1, t 1 to 2. So this will be I is equal to 1, I is equal to 2. If you do this, you will get AI at y. You can try it.
So what you're trying to say is like, what would be my second column of DH parameters?
Here
Uh,
is a DH table, no?
yeah, only
See,
one thing we wrote, right? Can you just come down?
here one, another one.
No. We are not checking for that problem, for the below problem.
Okay.
Here we have only one row, right?
Yeah, one row. I have made
1990 D.
arbitrary. I have made it arbitrary. It's not that there is no values for this. This is to get to this particular transformation matrix. This is not a problem we have solved. So there is no values for it. Okay.
Why?
Nevertheless.
No, no, no.
Okay. Let us.
Only the D and A values which you have put, that is like, okay, just take it as X and Y. But theta to alpha to it is true, right? 90, 90.
Okay. Uh, okay. You tell me the parameters. We'll do that way, right?
Okay.
Because I have done
Let
two,
us say
three
for the
transform.
same frame, uh, ZI minus 1, the offset one which you have
No,
drawn.
no. You just tell me the parameters. Straight away, tell me the parameters. Let us work
Okay.
that way,
Okay. So
right?
9 theta I, DI, AI,
Alpha I,
alpha I.
A.
So it is like
What are the
90, some D, A, and 90, right?
sorry? DA.
I mean, just take some values, okay?
Okay, DA 90,
Yeah. This
right?
is what our transformation, right?
Okay.
Remove the intermediate one. We have only
Okay.
0 and 1 frame.
Remove intermediate one. Okay. So let me take a frame like this. Z1,
Okay.
X1.
Okay.
Okay. Now you are
Yeah.
telling me that I am doing 90-degree rotation about
Uh,
theta.
yeah.
So my uh, X2 will be like this,
Okay.
right? About X2, I have done another uh, positive 90,
Hmm.
right? Z2 is here. Okay. That's good.
Okay.
Okay. Now you are telling me that uh, D distance it has moved is D. Okay. Then we have made another mistake. Right here. Right. It has also moved A. Okay. X2, D2. Sorry. Z2. Okay. This is what we have done. Correct?
Wait. We got our X. And then again 90, right? Z2 will be in the along Z1.
No. No.
What? Uh, First we
See
rotated.
here about Z1.
Yeah.
So my X2 will
Z.
be like this.
Yeah.
So X2 intermediate frame of Z1 will be like this. About X2, what we have done, rotated 90, we have got here,
Acha,
right?
acha. Yeah. Yeah. My bad. Sorry.
Yeah.
Yeah.
So this is following the transformation matrix that we have made. Uh, According to ground frame,
Acha. So
X
this
is
is for
A1.
this rotation you are telling.
Sorry.
This is for this rotation.
Yeah,
I mean,
this is for
for
this
this transformation.
transformation only. Yeah. So now I have moved A and I
Uh,
have moved positive D in Z axis, right? So this point, if I have to put it in 3D space, will be A0D. Yes.
yeah.
So what do we get it here?
Okay.
A0D.
Okay. So the transformation matrix which we have derived
Yeah.
is not for the thing.
Not
This.
for the thing that, not for the problem. See, it is for the,
Okay.
you can use this for the problem, but the problem is one more frame, no, here.
Okay.
So you have to account for that frame also. Then that will come as T0 to 1, then T1 to 2, and then you will get something called T0 to 2. And in that fourth row will nothing be the direct kinematic of
Acha.
your robot. Okay.
Okay.
Minimum set of kinematic parameters needed to specify the kinematic configuration for any n-axis are 4. That is joint. Is it correct? Pratyush, yes. I'm sorry I missed your question. Yes. These 4 are enough to do it. Since we are constructing our frame, these 4 are enough. That's what I will put it. But let me put an interesting problem in crystallography. You sometimes may not have orthonormal axes. At that time, certain rotation you cannot have. This crystallography is away from robotics, right? So you may not have those kind of liberty, right? At that time, you may have more parameters. So this is what I put forward. Yeah. So is there any more questions?
Yeah, like
Sir,
from the week one.
Yep. One second.
Yeah.
Yeah, Raman, go first.
Okay. So from the week one, I had this question from long time. So
Okay.
when we pre-multiply a rotation matrix and post-multiply it as a I mean that rotation matrix is being operated as a operator. So
Okay.
pre-multiply and post-multiply.
You're telling
Pre-multiply.
Rx, Rz, and RZ, Rx, something like this.
Okay. No, let us say like okay, you can put it that way, but my doubt was like suppose I have an orientation which takes me from mobile frame to fixed frame.
Okay.
Now I'm trying to use an rotation matrix, let us say about x-axis by 90 degrees. Now if I pre-multiply it and post-multiply it, the effects, I mean, one will be rotated about the fixed frame, the pre-multiplication x-axis, and the other it will be along the fixed mobile frame x-axis, right?
Yeah, that is
Post-multiplication.
correct.
Yeah. Uh, but I cannot comprehend it, like why it happens like that.
Look at it this way. So the moment we do this kind of a multiplication, right? So let me just work here itself. Okay. When we do this kind of multiplication, uh, what we are doing is when we do Rx and then we say Rz, what we are essentially doing is a sequence of rotation, right? So
Yeah.
now, when you do a post multiplication, like something like Rx, Rz,
Mm,
right? So this what it does is that this is from ground frame.
mm,
From ground frame, it goes to another frame. From that frame, only X is rotated. So this is different from this one, and that's why fixed and mobile frame you can relate that way. Now, the moment I have a frame, if I do Rx, then Rz, right? What I
mm,
do is that I am rotating Rz about the mobile frame only. If I get a new frame, right? So now, if you tell me that I do pre multiplication, whatever term he has used, Rx Rz, that means that Rx is now being done in mobile frame,
mm,
right?
mm,
So
mm,
this is the understanding behind that uh, entire thing.
mm.
Yeah. So is that it answers right your question?
Yeah.
Okay. Pranav, go ahead.
sir,
Yeah. Tell me.
sir, I did the operation you told, but I got somewhat similar answer, but not the actual.
Okay, so you can do one thing. You can see my previous lecture. Okay, in that I have shown how we have taken a problem where we did your roll pitch. Okay, we
Yes,
did a
sir.
your roll pitch rotation, and we have got the correct answer as per the assignment. So you can go through that lecture video because I think this is especially for week two. Taking week one question I can do it, but going ahead and solving it after 5:30 would be little tedious. Okay, Pranav. So I would just suggest you can go through that video, and I have given the presentation. Sorry, my drive link. Right, you can see here 1713. I have posted a drive link.
Yes,
You
sir,
can
I
go
saw it.
through that. There is a MATLAB program that does your role pitch.
Okay, sir.
Okay. So you can also look into that once. So probably you'll understand that a little better, or it can help you solve your problems also. It's a your role pitch. Okay, don't confuse with your pitch role. It's different. Uh,
Okay, sir. Sir,
but
that's just shuffling, no, sir.
sorry, Pranav.
Ya pitch roll means we first multiply ya and pitch and then roll. That's the meaning, no, sir.
Your pitch role means first you do X rotation, sorry, Z rotation, Y rotation, then X rotation. So your composite rotation matrix will come like this: RX, RY, RZ. I am sure that in the lecture he has given a composite rotation matrix format. So you can just substitute values there, no? Pranav?
Yes, sir.
You'll get. So just be careful. Is it written your pitch roll or your roll pitch? If it is your roll pitch, it's going to be our um, Atlas pitch, na? R Y R X R Z. Yeah. So this is the problem we have solved last week.
Sir, so we have to multiply in the reverse order of what we wrote.
Yes, that is what I'm telling you. Sequential rotation. So when we say your pitch roll, first you do your, not in the multiplication order. First you do your, after that you do roll. Sorry, roll. Right. After that you do pitch
Yes, sir.
or pitch and roll. Sorry. Pitch roll. Right. So when I do yaw first, like RZ first, anything I do next, like a pitch, will be multiplied this side, left hand side, right? Pitch y axis, z axis, x axis. Then I do roll. You get the order?
Yes, sir. I
Whatever
understood, sir.
subsequent operation will fall to the left. Whatever I do, right? It will fall to the left. Because what I am doing with pitch is nothing but I am pitching the entire frame that is transformed. Then I am rolling the entire frame that was transformed with that pitch.
Yes, sir.
Yeah? Now you get it, or what is happening?
Yes, sir. I
So
got
that
it, sir. Thank you, sir.
Rx, Ry, Rz. So if you don't follow this order, you'll get something else.
Yes, sir.
Okay. Any more
Thank you, sir.
questions? Yeah. I think I'll close the session. I'll stop the recording at least.